Okay, so we're live, Jim, as far as the cameras are concerned? All right. Well, welcome to this session of the Ottawa Astronomy Workshop series. I'm going to leave Tim to introduce what he's going to be talking about. But for those of you that don't know, we've suffered a tremendous loss in the last week or so. Eric Kuyara, who was our videographer, not only our videographer, but also did all of the videography for the RASC Ottawa Centre. He passed away, I believe it was the weekend before last.
Yeah, last Sunday.
And I just wanted to say a few words, because Eric has been such a support and a pillar of this particular series. Not only is he a loss to all of us, he's a loss, frankly, to astronomy in this city, to amateur astronomy. Eric was a volunteer. He's a professional videographer, but he decided one of the most important things to do in amateur astronomy was to get the word out, to get the enthusiasm out there, to teach, to make it an educational experience. And in this modern world, if you really want to get to young people, you've got to be online. And this was Eric's really major contribution to us. He did all of this for free. He would turn up with all of his equipment way before anybody turned up at the meeting. He'd record everything. He'd make sure that everything was working as it should. He'd trouble bust. And then he'd be the last one out of here. Not only was he a great videographer and frankly a great friend to amateur astronomy, but Eric was a great enthusiast. He was incredibly enthusiastic about astronomy itself. He had all kinds of projects that he wanted to actually put together as presentations, not just recordings of other people, but his own presentations. And you know, most importantly, Eric was just an all-round great guy. Whenever you interacted with Eric, there was a smile. Whenever you interacted with Eric, there was enthusiasm. We were going to get things done. We have to think of Eunice, his wife. My thoughts, our thoughts are with her. And the last thing I'd say is, you know, someone like Eric, you don't replace Eric. Eric will always be our Eric. Thank you. I'm going to hand over to Tim.
Yeah, with that intro. Yeah, he'll definitely be missed. What can I say about that? Well, I don't recognize all the faces in here. Some are completely new to me. Some I kind of remember the faces, but I can't put names to them. I'm not sure. I guess some of you know who I am. But not everybody, I guess. Anyway. Does anyone want the quick 2-minute, the quick 30-second bio?
Yep.
Okay. Let's see. It all began back when I was a little boy. No, never mind. Actually, it almost did, because I'm an Apollo era kid. And yeah, I still remember all the names of all the Apollo astronauts. A little fuzzy on Skylab. But yeah, so for the Apollo missions, I was looking with my little telescope, looking up at the moon. And I actually didn't even see the man in the moon until I was in my 20s, because I'd spent too much time looking at it through a telescope. And I was out on a date with who is now my wife, and oh my God, it's the man in the moon. And she looked at me rather oddly. Well, yes, I thought I'd never seen it before. What? Oh, then she married me anyway. Damn fool. Anyway, I'm trained as an engineer, and about 25 years ago I discovered I hated engineering, and I've been working in writing and illustration and education ever since. I've been associated with the Science and Tech Museum in Aviation for quite a long time. And part of what I like to do is public outreach and basically trying to familiarize stuff for, well, I hate to sound snarky, but you know, kind of everyday people. People who aren't necessarily doing this because it's a degree program, but because they think it's just bloody cool, which is pretty much where I am. I think I took 2 astrophysics courses in my life. Everything else has been from reading the massive piles of books that are in my office, on my bookshelves, on my floor, in the bookshelves downstairs, piled on top of the piano, and I think holding up part of the dog crate. So that's where the background on this is. That's where I come from. For my sins, I let myself be turned into the president of the Royal Astronomical Society Ottawa Centre, which means I was too damn stupid to run away when they found me. And I still have another year of my sentence to go. So there you have it. I was asked if I could do something on nebulae, and that's as I said at the last RASC meeting, my plans were truly nebulous, because, I mean, what do you do with nebulae? I mean, there's a lot of stuff in there. So as I was putting this together, I sort of started getting very interested in the structures. All these neat little shapes. Now, we've gone over in the sessions before, things like stellar evolution. So you're aware of how important nebulae are in terms of star birth and star death and cosmic recycling. But the structures are pretty cool. What we've got here is the Western Veil Nebula, or the Witch's Broom, depending on how you want to call it. And there's an awful lot of really delicate stuff in here. And there's some surprisingly interesting interactions that go into how it works. What I wanted to show you here was the rosette. And I can see already my slides have gotten out of order from what I wanted, but that's okay, I'll work with it now. The Rosette Nebula, and moving ahead, this little beauty, which actually was only discovered a few years back. It's called the Necklace Nebula, as you can see from the sign. And what's cool about these is we actually, oh, stop this. You're going to really cause me trouble here today, aren't you? Yeah, this is not going to be my most polished presentation, obviously. Where's my slide sorter? Ah, there we go. Holy snikes, this really got all whacked out, completely whacked out a mess. Oh dear, where's my diagram? Ha! Well, I'll have to show it to you off the screen. Well, not on, I mean, it'll be on the screen, but it won't be in the presentation, because somehow I skillfully deleted the silly picture. Oh, stop that. Behave. Where am I? Oh, yeah, probably under documents and presentations and nebulae. And I had a really terrible joke lined up for this too, which makes it even worse. That really makes it painful. It turns out that oh, stop that! Open the freaking file! Thank you, you magnificently massive pile of parrot. No, open! Thank you.
Well, at least you didn't throw it across the room, that's
No, I try to avoid that, partly because it's a fairly new computer after I did that to the last one. It turns out that we can make a fairly good assumption. We can make some fairly basic assumptions about what's happening in nebulae from some surprisingly simple basics. And I'm going to start here with a concept called the Stromgren sphere. In 1938, an astronomer named Brent Stromgren came up with a set of assumptions. He was looking at what happened to nebulae around very hot stars, Class O and Class B stars. And he started coming up with a series of assumptions that were very simplified, but it turned out to have some remarkably powerful implications. He came up with a couple of basic assumptions, and this leads to the question you had, is what's in a nebula? One basic assumption we can have is that a nebula is basically hydrogen. Now there's everything else in it. I mean, you've got every metal, every material known to mankind. You've got a lot of hydrocarbons. You've got enough ethanol to produce pangalactic gargle blasters for, you know, the whole galaxy. But it's basically, primarily it's hydrogen. We can also, from there, decide that there are two types of hydrogen that we have to deal with. Ionized hydrogen, or H2. If you're not familiar with that terminology, it's old spectroscopic terminology. H1 is neutral hydrogen, H2 is ionized, or really protons. Now, what that means is a couple of basic things. With a gas this simple, we now have a simple formula for the speed of sound. Now, you wouldn't think of the speed of sound, because the first thing we hear about nebulae is, well, it's better than the best vacuum we can make down here on Earth. And it is. But the speed of sound is still significant. Stuff still propagates through that material. It turns out for a hot H2 region, the speed of sound is going to be around 2,800 meters per second. And out here in the cold H1 region, it's going to be about 200 meters per second. So that was the first of his simplifying assumptions. The next simplifying assumption that Stromgren made was that the regions are effectively isothermal. In other words, it's the same temperature throughout, and as long as you're far enough away from the ionizing star, it's not a bad assumption. It's not the world's best, but it actually is not bad. And so we can simplify this again. The temperature inside the H2 region for a Stromgren sphere is about the order of 10,000 kelvins, and in the H1 region around it, it's about 10 kelvins. Now here's the really wild part. It turns out that from Stromgren's analysis, we can actually see an ionization front around that tightly binds the H2 region. It's for all practical purposes, it's a membrane. Because it's of negligible thickness compared to the overall size of the nebula. And the interesting part is inside this red H2 region, inside the red H2 region there, you're getting a lot of photoionization. In other words, you're getting all the ultraviolet and shorter wavelengths coming off the central star that are blasting the electrons off the material, predominantly hydrogen. And there is a certain amount of recombination. In other words, we are getting a certain amount of neutral hydrogen forming. But the interesting part is there's very, very little of it until we get past a threshold. And this was Stromgren's real thought was, well, it's got to stop somewhere or everything would be ionized. So what he ended up discovering is you've got a region where you're going to start seeing a big shift between the photodissociation into the ions and the recombination back into it. And it turns out that the boundary where you go from mostly ionization to mostly normalization, mostly recombination, is incredibly thin. And in fact, negligible size in terms of the front. Which means you've got a couple of really interesting things happening. Not only do you have a very well-defined region between the two ionization states, but you also have a massive thermocline, an incredibly steep thermocline, which means an incredible discontinuity in the speed of sound. So flow that's inside the H2 region can be subsonic or transonic, and as soon as it crosses that ionization front, boom, it's supersonic. So now you get an instant shock front. Now, this is where I messed up my beautiful little presentation, because I know this is beginning to sound an awful lot like, oh, come on, don't be a pain in the patoot. Do what I want, you magnificently pile of crud.
You magnificently ignorant pile of parrot droppings.
Yes, open. Come on, be nice. There we go. I know, the Stromgren sphere is beginning to sound like a spherical cow. I don't know if any of you have run into the spherical cow before, but, oh, good. Basically, it's part of an old joke. If you ask an astrophysicist how to explain the behavior of cows, the astrophysicist will pause for a moment and say, well, first, let's assume the cow is spherical. And everything follows from there. The Stromgren sphere sounds an awful lot like a spherical cow. Yeah, what a stupid approximation. I mean, a spherical cow isn't too bad. I mean, it's almost as wide as it's high, so it's going to take this much room in a cattle truck. And we can assume they roll along the fields, and but it falls apart. The crazy part is the Stromgren sphere is actually a reasonable model for a lot of things. And the example, which I blew apart in my marvelously, carefully built presentation. Oh, come on. Be nice. Come on, slideshow. Yeah, thank you. Hello. There's a perfect example of a Stromgren sphere, the inside of the Rosette Nebula. And this one, discovered actually in 2006 at the European Southern Observatory, and then imaged by the Hubble Space Telescope, because they were able to get some short wavelength observations. The Necklace Nebula is another example of the Stromgren sphere. The central star in here is a very hot class O, if I recall, and we've got the classical central ionized area. And here you can sort of see where the bovine nature of the Stromgren sphere is coming to fore, because it ain't spherical. And there's some very interesting structures here in the edge, just past the ionization front. Now this I find really, really cool. So moving ahead, if you look back at those structures before, let's see, going backwards. Oh, wait a minute. Thank you. We see the structures here. And these are quite reminiscent of the structures we see in the Crab Nebula. Now, you probably stumbled into this before. You'll often read this, that the Crab Nebula is the example of Rayleigh-Taylor instabilities. It's a classic line. So what the heck is a Rayleigh-Taylor instability? Basically, it's what happens when you accelerate a gas, or a fluid, I should say, into a denser fluid. And it doesn't work that well. You end up getting jets. So if we move ahead here, oh please, oh thankfully this went in the same place. We see now that these fingers leading inwards are in fact the Rayleigh-Taylor effects. You will often find some books and some articles saying the tendrils leading out are Rayleigh-Taylor fingers. They're not. They're different beasts. Those aren't from Rayleigh-Taylor instability. If I move ahead here, oh please be the right spot. Here we go. The Helix Nebula, another lovely example. Here in visible light, it's pretty, but if you look at the infrared, take a look at the fingers leading inwards. Those are Rayleigh-Taylor fingers. And if you look very carefully at the visible light, they're there once you know what to look for. Now the crazy part with these fingers is you might think that what's happening is the gas coming from the inside is simply going past this and leaving it behind. Not so. The fingers are actually being pushed inwards. They're actually moving inwards. Now, here's one of the classic pictures. We have over here the classic picture of Rayleigh-Taylor instability, and this one is actually a computer simulation. You can do this with the classic bit of putting a little bit of food coloring on top of water, and you'll have the slightly higher density food coloring. What Lord Rayleigh started working with this in the 1880s. What Taylor's contribution was, and you can see it here in the right-hand picture, Taylor's contribution was to recognize that the buoyancy that's putting up the lighter fluid can actually be interpreted as acceleration into the dense fluid. It's backwards to what you think, because you think of gravity pulling the dense fluid down, and it does, but Taylor's contribution was to recognize we can model the other fluid coming up as being accelerated. And in fact, in this case, this is oh, sorry, I'm pointing the wrong thing. In this case over here, this is actually horizontal. This is not a gravitational flow, this is a horizontal flow. And you're accelerating the yellow fluid up into the blue. And you can see the tendrils that are forming here. So if we back up a bit, we can start seeing where the Rayleigh-Taylor fingers are. I keep going back and forth here. We can see the Rayleigh-Taylor fingers forming quite nicely from the inside. Right here we've got this hot ionized gas coming out from the supernova remnant right in here. It's past the ionized region, past the thermocline, and here we're getting a humongous shock front. And because we've got the shock front, we've got a huge mass of piled up material of quite high density. And since that piled up material is high density, as this lighter material from the inside is slamming into it, we've got the proper recipe for Rayleigh-Taylor instability. And as we saw from that other picture with the yellow, the material is actually swirling back in and slamming the jets inward. For your piece of useless trivia, this was actually a major problem with the development of the Fat Man nuclear weapon, because when they were working on the implosion technique, you had a little problem. You were slamming explosives, fairly low density, into a high density chunk of plutonium, trying to compress it to something the size of a walnut, and you're going to get jetting coming backwards from it. So one of the ways they got around that was by wrapping the whole thing in a blanket of uranium-238, which was pretty much as dense as the plutonium, and that's what got rid of the Rayleigh-Taylor instability. They used brute force and ignorance on top of a solid sphere of plutonium. So anyway, I'm digressing. That's the other thing I'm interested in, is nuclear history. Yeah, I know, too many hobbies. But here's the funny thing with Rayleigh-Taylor instability. It also leads to these marvelous little things. These marvelous little structures, globules. And these are called eggs, evaporating gaseous globules. And it turns out that the Rayleigh-Taylor instability does not just give you the fingers. I know, that sounded awful. It doesn't give you the finger. Yeah, never mind, stop it. So what actually can happen here is that the swirling can get so extensive that we start biting off a little chunk. And we can actually end up with a separated piece. Now here the red is showing fairly low, the color of the red is showing increasing density. So here we have an ionized region, so this is basically H2. We have an unionized region out here, and as the ionizing radiation is coming up and pushing the shock front ahead, yeah, okay, it does go backwards, good. We can see here how we're actually removing the shock front out, but at the same time we're also slamming a finger in, but we're actually slamming it hard enough to separate. And this is where we get stuff like globules, and if you ran into proplyds in the Orion Nebula, that actually all comes out of RT instability. Now, this is a collage which the European Southern Observatory called Pillars of Destruction, and it's a play on the old Pillars of Creation picture. Because that's what these things are. These are basically bits of nebula that are being destroyed by the stars that are forming. And if we take a look here, we've got an awful lot of stuff here. Take a look at this one. Now, doesn't that look like that little diagram I showed you before? And we have one that's going to come out of here, and some other ones that are going to come out of here. So we're seeing an awful lot of that Rayleigh-Taylor instability, but in ways that you wouldn't have expected. At least I didn't expect it when I was preparing this. But that doesn't cover everything. Here's a really cool area, the Carina Nebula. It's a fabulous star-forming region. We've got some lovely star formation here. But take a look at these patterns in here. Okay, maybe we can cover this with Rayleigh-Taylor, but that doesn't really work for it, does it? At least it doesn't for me. So here's another example, Barnard 211 and 213. I don't know if you're familiar with the Barnard series of nebulae, but these are all dark nebulae. All the Barnard nebulae are dark ones. This is a molecular cloud in Taurus, and what we see here is visible light, and this is imaged with submillimeter. So this would be stuff like the James Maxwell Clark Observatory in Mauna Kea and facilities like that. And here we have the same kind of wavery structure that we kind of saw back there in the Carina Nebula. It turns out, I stumbled into this one before, and this is a stability I'd never heard of before I decided to come into this one, and it's called Vishniac instability. And it was actually first described in 1983 by a fellow named Raman Vishniac, whose father actually turns out to be an internationally recognized photographer. So if you've run into the photography by a guy named Vishniac, it's the same family. And it turns out that this is an instability that comes out of the boundary layer between an H2 region and an H1 region. And here's one of the classic examples. This little beast is called the cometary globule, purely for the visual. This has nothing to do with comets. First one of these was discovered by the European Southern Observatory at Cerro Paranal in '02, I think, if I recall, somewhere around '02 or '03. A fairly recent discovery of this class of globule, and it turns out to be the poster child for Vishniac instability. What we have here is we've got the H2 region, which is pressing in on the boundary layer by virtue of you're going into the boundary layer. But in here we've got thermal pressure on the inside, and so far looks all cool. We've got this boundary layer, and we've got the two forces combining. But an interesting thing happens when you get a little tiny bit of distortion in it. This is where the instability bit comes up. We discover that the pressure coming in from the H1 region is always in one direction, but the thermal region is always at right angles. Is always at right angles to the boundary. And this is producing density gradients. So here we have fairly high density, here we have a fairly low density. Material is going to flow in that boundary layer. And it turns out that with the Vishniac instability, we have an oscillation. And in addition to just oscillating back and forth, it'll also spread out from the motions in here. And all this comes out of the fact that we've got always one direction from the H1 region, but only perpendicular, only normals from the, excuse me, from the H2 region. So here we have another form of instability that's explaining a huge mass of different structures. For example, this one. Here you can really see it. Once you see Vishniac instability, there it is. And you wouldn't have seen it without the submillimeter imaging, because it's buried down here in the guts of the molecular cloud. And here, in the Carina Nebula, with the star-forming regions back here, we're looking at another bit of Vishniac instability. There's a hot star here. It's actually blasting some of this towards us. And there's a bit more pressure coming in here from the back. So it's a really complicated three-dimensional thing. And it turns out that there's still some pretty active work being done on this form of instability.
Tim, can you go back to the that slide there? It's worth pointing out here that for all of these instabilities, although you zero in on one instability, when you actually see them in 3 dimensions, they're periodic.
Oh, yes.
Now, it's not perfect, it's statistically periodic. And one of the early slides that Tim showed with that sort of necklace nebula, if you will, those bright points, they were almost equally spaced all the way around. And so looking at this particular picture, this tulip here, this cometary globule, you can actually see the periodicity beautifully laid out there.
Yes, you can. That's why I grabbed this one as the poster boy. It's beautiful for this. And this, you should be able to, in principle, find out the resonant frequency for this, but I couldn't find that in any of my references. But that would certainly give you the extent to which it's going to spread out. One of the cool things is the book here. The book for this one described a lovely little model you can use for Vishniac instability in a classroom, which is to take a piece of paper and crumple it, and then smooth it out. And then what you've got left are the bumps and waves. And it all comes out of the fact that you've got forces from the outside, you're pushing in on it, but from the inside, as you're crumpling it, it's always going out at a normal to the paper. So it's really kind of cool how you can get a simple thing that will demonstrate.
Can I ask a question?
Yes, of course.
So what determines the shape of the boundary?
Sorry, the curved shape?
Yeah, I mean, and the actual shape, because
Oh, over here? Or over here?
both, I guess.
Okay, this is, of course, this is a highly stylized drawing. But the instability does produce this kind of, how shall I describe it?
So there's thermal pressure from the inside.
Yes, there's thermal pressure from the inside and ram pressure from the outside, just by virtue of slamming into the medium.
Okay, so there's basically fluctuations that initially distort the
Yeah,
surface.
and something is going to put in a little bit of a ripple.
That's right.
There's another way of explaining this, which is that if you start with a planar surface, and if you begin to allow it to distort,
so it's,
plus the periodicity that I mentioned,
Yes.
then that determines that the curve has to actually correspond technically to either a cosine or a sine wave.
A sine wave, at least to a first approximation.
Exactly, and so that's why you get this smooth curve rather than a pyramid, for example, or a pointy shape. It's the periodicity spread throughout the surface results in this statistically, at least at the beginning.
Yeah, but the interesting part, though, that's been done with the Vishniac instability, and this one actually showed in the Western Veil Nebula, is that this periodicity actually persists for quite a long time. It spreads out, but I mean, it gets distorted naturally by a million other factors. So what you're seeing here is that basically the planar structure, or this could also be a very gentle curve, you know, it'll work both ways, but that structure is actually a very unstable thing. Anything will throw it off. And thank you, because you put together a beautiful explanation, Simon.
But Tim, I don't understand, why does the H2 region rise perpendicular to that front, or whatever you want?
Right. Basically what's happening here is the ionized region is pressing out in all directions. It's pressing in all directions. The ram pressure, you're basically slamming into, there's no effect here. There's nothing pushing in on this. This is a shock, oh sorry. This is a shock front here, So there's no way the information about what's happening here can propagate back into the H2 region. Yeah, because basically, yeah, and that's a good observation. Basically, there's a no-slip condition here, but there isn't here. Partly because you're dealing here with a shock front.
Yeah.
Information cannot propagate inwards.
Yeah.
The only way the information from the shock can propagate is outwards. This is becoming supersonic, and the thing with supersonic is you always hear the classic one. You know, people describing being in a Concorde. You couldn't hear the engines because you're ahead of them. And it's the same deal here. This material back here has absolutely no way of gathering any kind of impact, literally, from this shock front. So this is pretty much free to go any way it is. Up here you're constrained. This is a shock wave that's blasting outward. And this can't react. But you are actually, part of the thing here is you are dealing with a different pressure front, and this is what I've tried to show here with the different colors. You're seeing density variations here. And take a look what happens in the next part of the oscillation. Oh, stop that! Behave! As we go back and forth between the two of them, take a look what happens to the density variations. And with that, what we can see is that material is actually sloshing back and forth. And in the process of sloshing back and forth, the very edge membranes aren't moving, but inside there's a tremendous amount of motion. But again, the information can only propagate outwards. So this can't know what's going on further out. This does. I know "know" is a bad term, but it's a convenient reference. Yeah.
Sorry if you don't mind me asking.
Not at all.
Question. You spend a lot of time on this
No.
slide. The description of the image on the right as a tulip, which
Yep.
I think is very
Yeah. In
appropriate.
fact,
This
it's
is
called.
all
In fact, it's called the tulip nebula.
okay, and so it's emitting from, I guess, more or less a single source in the
Yeah.
middle.
Yeah. There's
Okay.
there's actually a source. It's if you see the whole picture, it's actually somewhere down around here.
Okay, so I mean, one would expect then that it would be like a 360-degree globe around that
Yeah.
source.
You would.
So how come is it open so that we can sort of look down into the tulip?
This one this one is a selected chunk of the whole massive nebula. This is part of a huge star forming region.
Oh, okay.
This is one. I mean, this is the PR picture that the ESO picked.
Right.
So they picked the one that is showing the best. I grabbed this because this is the one that actually did the analysis of the edges here as Vishniac instability. But the thing is all that is discussing is just this tiny little area down here. We've got a bunch of other things that are happening
Okay.
down here.
Okay.
So there's a tremendous amount going on in that particular chunk of nebula. And that's what makes this a little complicated, is because every little bit of it works independently, which I find very cool. I know, I said that a lot. This is an interesting one. Here we have a nice star forming region. And as I say, this is ripping the nursery apart. HH here, by the way, refers to Herbig Haro. These are newborn stars. These are the markers of newborn stars. You see here, you have a shock front from an ignited star. Here's a shock front from an ignited star. Here's the shock front around an ignited star, which is probably in here. And what we've seen here is that the nursery is in here. The effects of the igniting stars are actually pushing the nursery apart. These are actually impinging on each other and blasting. This is basically a low density area. We've got two high density areas here, formed by the interaction of the merging stars. And this is partly where the ESO referred to the pillars of destruction. These things are ripping the nebula apart as they're forming. The interesting part, though, is these little puppies are outgassing at staggeringly high rates. So they're actually taking an awful lot of the pre-burst material and mixing it. And so what we're doing is we're enriching the medium to a slight extent. Not much, because there's not much reaction happening here. This one I just love showing. This is a Herbig Haro object in the constellation of Orion. And this is actually one of the first ones studied by the European Southern Observatory. I checked recently, they still do not know what the waterfall is. There's no explanation of the waterfall. But take a look at this. This is, I think the glass here. Yep. This is a shock front from an ignited star. And what you're looking at is a foreshortened circle.
Yeah.
You're seeing a foreshortened circle. Doppler measurements can show that these shock fronts here are actually moving at about 250 kilometers a second. And you can see here that there's a jet that's been blasted out of the igniting star. Best estimate is the star that's in here, clouded by gas, is probably no more than 30,000 years old. If that. And this is forming itself into a T-Tauri star. This is actually showing that wonderful stuff that used to be called nebulium. I'll get to that in a sec. But this is basically hydrogen-3. Oxygen-3, O3. So what we're seeing here is a brand new star, and we're seeing the effects of the shock wave from the star's ignition.
Mm.
Now this star is going to oscillate like crazy for probably the next million years and become a classic T-Tauri star. And the next stage after that comes with the really rude name of Fu Orionis. No, I saw that. I was going to, I was doing a talk to a bunch of like grade 9 kids, and I said, well, but are they all T-Tauri? And I flipped through my notes and said, well, no, they're also no, they're not all T-Tauri. I'm not saying this one to grade 9 kids. No, absolutely not. And it's Uranus. Now this one's beautiful. This is a fairly recent discovery as well, the Southern Owl Nebula. Isn't that lovely? But look ahead. This one's the Cat's Eye Nebula. And this is one of my absolute favorite nebulae for a bunch of reasons. Not that I've seen a very good view through my telescopes, because I haven't. But take a look at this. What we have here are nested shock fronts. And apparently, the eruptions from this star, when it was in its late red giant stage, were coming out about every 1,500 years. Very periodic. So what we're seeing here are multiple shock fronts with unshocked material in the middle. And here we've got some incredibly elaborate jets coming out from the inside. And who knows what's going on in here. Probably some Rayleigh-Taylor instability here, perhaps some Vishniac there, I'm not sure. You'd have to do some pretty hefty analysis. One of the reasons why this is a very fond nebula for me is I'm very interested in spectroscopy. This was the first planetary nebula to be analyzed spectroscopically by William Huggins. And what he discovered was a set of lines that didn't correspond to anything known. And just recently before that, helium had been discovered in the sun, hence the name helium. So Huggins assumed that, well, there's a new material called helium, so there must be a new element here that he called nebulium. What Huggins and nobody else knew at the time is a little nasty thing called forbidden lines. These are transitions in energy states that by old physics were completely impossible. But when you looked at it with more refined quantum physics, it turned out they're not impossible, they're just freaking bleeding unlikely. And they've never been recreated on Earth because they require that lab vacuum, and they require untold millions and millions of ionized atoms, so that every now and again one can just say, I'll make the transition. I don't care if it's forbidden, I'm going to do it anyway. And it turned out to be O3. So I love this thing for a whole bunch of reasons. It's got such a fabulous structure. You can see the multiple shock waves, and it's the original analysis where Huggins was able to verify that Herschel's original estimate of a planetary nebula was actually quite correct. Herschel speculated that what we had here was a luminous fluid instead of a star. And Huggins was able to demonstrate that, yeah, that's what this stuff is. It's a luminous fluid. It's actually glowing from the effect of what we now know to be a white dwarf stuck in the middle of that star. Now, these are...
Go back to that picture, because that's absolutely fascinating. I'd never even seen this.
Yeah.
But you can actually see the very fine radiating fingers,
Yes.
the Rayleigh-Taylor.
Yep.
But no, I'm not thinking there.
Mm-hmm.
Here.
Oh, yes.
Radial.
Oh, yeah.
Look where they are. They're
Oh, yeah.
in They're in the outer shells.
Oh yes, they're in shells upon shells upon shells upon
But in
shells.
the inner shells, you don't see them.
Well, right here in the very inner
But
one.
in the inner
In
shells,
very inner
instead
one.
of seeing fingers, you're seeing blobs.
Yeah, well, you are seeing blobs, and
Yeah.
so you're getting multiple.
But remember that the shape of a Rayleigh-Taylor instability
Yep.
is a function of the viscosity contrast
Yes.
between the two materials across
Yes.
the interface.
Yes.
So all you need is less of a temperature difference in the latter part
Yep.
to get these large blobby shapes.
Yep.
Whereas if things were really hot in the beginning part,
Yep.
that would give you these very, very fine fingers.
Would give you the
because that's
fine
way it
fingers,
goes.
yes. Yep. So you've got a nice combination here. You've got fingers, and you can see the blobs forming here at the end,
Yeah.
and the little fork shapes that you'll often get
Yeah.
as an alternative to the blobs. So yeah, lovely observations. Perfect. This is one I can stare at forever. This is the nicest picture of the cat's eye that I've ever been able to find.
You can see some of that structure in an amateur telescope too. Say 12 inches and up or something.
Yep. I've had very bad luck with it myself, but could be
I
that.
actually saw it on an 82-inch.
Yeah, okay, I don't feel so bad about not getting it with my 8.
It was like Observatory in
Amateur.
Texas.
Yeah, amateur. Yeah, amateur. Boy.
I hate to tell you, but I've seen it with beautifully with a 6-inch and a Malincan
Yeah.
with the detailed structure. Not that kind of detailed structure, but multiple shells.
Oh, shut up. I have actually, I've never tried it. I've only tried it naked eye, which, considering I have keratoconus, is a very bad idea. Think of astigmatism on steroids.
Well, we're also too old.
Oh, trust me, no, this isn't necessarily a young thing. I don't know why I put this in. I really can't explain much about it. I just like it. This was actually one of the first things I imaged with an astronomical camera. Was Thor's helmet. And it was actually one of the I should say it's not one of the first things I imaged, it's one of the first things I imaged that I was willing to acknowledge. I had plenty more things that I'd imaged, but I wasn't, other than the moon and stuff like that. But, again, what you are seeing though here is explosive, or if you like, impulsive reactions from a very, very hot star that's doing a tremendous amount of outgassing. Which leads me to this little beast. Another marvelous little example that we've had right next door, supernova 1987A, and it's right in here. And I put this large scale on here because it's got the scale on it. So here's galactic north, galactic east, and you can get the size of scale here. So we're looking at, probably 3 or 4 light years across. And here's the close-up of the rings produced around supernova 1987A. What these are is, they have a look of interlocked rings, but you're actually looking at a bipolar structure seen at an angle. So think of an hourglass looked at from a bit of an angle. What was interesting here, let's move ahead. Oh boy, I am really wonked out of shape here. Man, I'm just cooking with gas here. Oh, stop that, behave. I do have a little video showing, and I'm not even gonna try doing it except from here, and oh boy, this is probably gonna tell me. Oh, what? What's this? It's actually gonna try to show the video? Be still, my beating heart.
It's loading it up.
Yeah, be still, my beating heart.
These are actual images?
Yep. Yep, this is actual imagery from, if I recall, the Sea Observatory. And so we can actually see this forming. The prediction that came with this one as well, with the news release, the press release from the European Southern Observatory, was their assessment is that this ring will probably disappear somewhere between 2030 and 2050. So we're actually watching evolution of the debris from a supernova. So we may not have had our big beautiful Tycho star supernova or Kepler star supernova, so we didn't have that beautiful light in the sky that lasted for months and months and months, but we do have a little lab right next door. And that is just a way cool thing to see.
There was that periodicity again.
Yep. And that led them to produce this beautiful little 3D model. I hope this will do something. Let's try Earth and View. I think that would do it. Yeah, there we go. Animated GIF. And it's too damn fast, of course.
No, it's visible.
Yeah.
You can see it.
Yep.
Yeah.
So this is not artist's conception. This is actually animation from the data that we're seeing back there in the previous one. So this is actual animated true data as opposed to an artist representation. So you can see there's some pretty complex stuff happening in those. One of the things I find interesting with the supernova is up until I think somewhere around 1996, we were still able to see the results of nuclear reactions going in that inner bright ring. So there were still high-end nuclear reactions taking place in there. So they're still producing things like what you were able to find were things of short-lived, fairly short-lived isotopes. A couple of the cobalt nickel, if I recall, that were fairly short-lived. So there's still our process nucleosynthesis going on in that ring for years after the detonation. So this is a fantastic opportunity. Now this one, looking deeper into the old Fager, this is a marvelous little instrument. This first went on Very Large Telescope Unit 4 in 2012. What this beast is multi-unit spectroscopic explorer, and this thing is a spectroscope on steroids. What this thing does is it takes a full 1 minute by 1 minute image, splits it up into 24 channels. Each one of those channels is examined spectroscopically in 48 separate slices. There's your example of the spectroscopic results. And what this gives us, now I wish they hadn't done this, because this sort of looks like big deal. It's tricolor imaging, so what? Except what they didn't show very well here is that this isn't just tricolor. This is actual full spectroscopy, down to getting the spectra of each individual, for each of those 24 channels and each of the 48 slices in each channel, you're actually getting a full-blown spectrum. And by selecting the wavelengths, you can actually get a really good 3D probe with a complete indication of the materials that are buried in the nebula. And they've been doing this for a few of them. And one of the fun things with that, oh, come on, please. This has been a new, an outreach effort done by ESO. They've actually written it up in their current messenger in CAP magazine. You can actually get the ESO messenger and the ESO CAP, communicating amateur astronomic. I can't remember what the CAP stands for, but you can get those magazines from ESO for free. And CAP goes in a tremendous amount to outreach, and Messenger gives you a complete update on what they're doing. And all I had to do was give them a business name. And I've been getting it free from them for years. They must have one heck of an outreach budget. But this is 3D printed slices of the pillars of destruction. So they've actually started producing 3D slices. So they're taking these out to school kids in Chile and putting these out on tables to show the 3D structure. And that 3D structure was pulled out of the Muse model that we saw on the previous slide. This was the nicest one that I found. Another one that came out of this was a beautiful, you can get the 3D printing files for the Homunculus Nebula. So you can get these files and print them out, and these are actually based on the actual measurements. So you can get these files and print them, and take them out to an outreach session. So here you go, hold your very own homunculus. So this is just way too cool. I mean, that would be nice, you know, take out something in here, hold this. There, that's what you're looking at. That's cool. Now that is outreach, literally. No, we need a 3D printer. Well, yeah, well, Science and Tech has got one now in the makerspace. So. Well, that was the end of my formal stuff. I assembled zillions and zillions and zillions of pictures. All right, dozens of pictures. All right, some pictures. What I've basically done here, folks, is I've walked you through my little voyage of discovery. So you're basically learning as I am. This is, I've been fascinated by the shapes for a long, long time. And trying to prepare for this, I kind of wanted to, okay, how can I explain the shapes? I know a little bit about RT instability, and I know a bit about the history of RT instability, but there's got to be more. And I'd remembered Stromgren spheres from an early astrophysics course and forgotten about it. And then when I realized the assumptions behind the Stromgren sphere actually give you a tremendous amount of material for understanding what's going on there. It may be a spherical cow, but it's a remarkably useful one. So I'm not sure I have much else to offer you, but if anybody wants to sit and babble and complain and throw rocks or whatever, let's do it. Sorry.
Well, what I will say is that you've given me personally a totally new perspective on these objects that I'm happy to look at through my telescope with or without a camera.
That's what I got doing
I
this.
had no idea that this was basically, idea of instability is yes, but I had no idea that this was a Rayleigh-Taylor like this.
Yeah. Yeah, I mean, fingers standard. Everybody says, oh yeah, Rayleigh-Taylor's fingers.
Absolutely fascinating.
It is cool, isn't it? I mean, it gives you a real, when you're, the next time you're going to look at these, even if it's a picture from ESO or through your own telescope or, you know, on a Mellencamp screen, I don't know, but for me, I'm going to see it differently. I'm going to see it a whole new light. And that, to me, is just the coolest thing out there.
Does that mean, like, for example, a supernova remnant,
Mm-hmm.
which, you know, as the star is going through its final stages of life, it's giving off its outer layers. So
Yep.
there's this cloud of neutral hydrogen sitting around it.
Yep.
Once the supernova happens,
Yep.
all that ionizing radiation is what's lighting up.
Yeah.
But that shock wave is moving through this cloud,
Excuse me.
and it's not necessarily going to blow this cloud outwards. It's actually going to go through the cloud.
Yeah, you're getting multiple effects. You are getting the shock wave propagating through the cloud. It's also moving the cloud outward. The problem is that you've got multiple reactions, as I understand it anyhow. You're getting multiple things happening. You are forming a shock front, and in that shock front you're getting, in the case of a supernova explosion, that's the frames of the video. The temperatures that we measured shortly after 1987A were in the tens of millions of degrees inside that shock front. Probably even higher, because it must have been higher than that, because they were seeing the results of our speak for crying out loud. Our process, the rapid nucleosynthesis process. So the temperatures had to be a lot higher in localized chunks, but they were measuring them in the multiple millions of degrees. So you are getting expansion just from having the bulk motion of the inside material, but you are also getting the shock wave forming. So the best analogy I could come up with that was looking at the shock front expanding from the nuclear explosion. If you've ever seen if you notice the videos showing particularly the Crossroads Baker explosion, which is the one they did on water. And you can see the shock wave propagating both in the water, and then the shock wave propagating through the air. Two different shock waves, and that's the best model I could come up with here. So you've got stuff that's happening inside that shock wave that is unshocked material, and a massive amount of interaction on the shock front itself, but then it's also propagating into the air beyond it. And I must confess, I'm having a little trouble getting my head around what's going on in those three realms. I'm okay if I separate the realms, but what's going on as a bulk picture is, I'm having trouble putting my head around it. Every time I think I get close to it, it falls apart. It's like, you know, Feynman explaining something and saying he didn't quite understand it. So if I'm sounding fuzzy on this, it's because I still am. and I'm hoping I will get a better handle on it. I was hoping maybe talking to you guys I'd have a better handle on it, because that often happens for me. I mean, you're seeing me here in my astronomical underpants. They're clean and fresh, but
it's worth looking at what the variables are.
yes.
You know, we tend to look at these things through our telescopes, and because we can't see them moving because they're
No.
so big, you go, okay, that's fixed. And if it's fixed, then maybe the parameters are fixed.
But that tulip
They're
nebula,
not.
but the tulip nebula I was showing you. See if I can find that picture. Here we go. That one, the discussion on this one has mentioned that you're watching changes in this in as few as a couple of years.
Yeah.
I mean, this is moving by astronomical standpoints. This thing is you know it's an eye blink. I mean, this stuff is changing in far less than human lifetimes.
So I guess it's because, I mean, what would be the conditions that would create Rayleigh-Taylor instability as opposed to Vishniac? It seems to me that
As opposed to?
Vishniac instability, it seems that you need speed for the Vishniac, right? If we're talking about ram pressure, you need movement.
Yes, you do
Right.
need movement. Yep.
So I think
But the Rayleigh-Taylor instability requires an acceleration of material. So
True.
they're both dynamic
But
effects.
that's primarily, the instability is primarily because of the difference in density.
Yes.
Right?
Yeah.
Well, the Vishniac one seems to be due to movement through the fluid.
As near as I can follow it, it's movement through the fluid, but it's the fact that we're looking at a sheet, a large and fairly cohesive sheet, in which we can actually see the movement of the material inside that sheet. I could be dead wrong on that.
The way I see it
Okay,
is,
I'm-
I mean, it's just
I'm all,
like
no,
I'm trying
no, I'm
to,
all ears.
I'm trying to make sense of it in my own head.
I know.
If inside the, that sheet you had like
Yep.
uniform conditions, you would have the spherical cow.
Yes.
There will be like an equilibrium at the
Yes.
surface, right?
Which you can't have.
Yeah, and because of different types of fluctuations, you have different types of instabilities
Yes.
that you see.
Yep.
So the Vishniac for me is kind of like the instability that you have in like a fluid, something moving into the fluid. So you have, and I mean, in this case, it's not a solid object. but you have
I think I see where it's coming from. I'm hoping this thing is going to cooperate with me. I think I see where you're coming with this. I think.
So you have like, it's not a solid object moving through a fluid, but you still have the pressure, which is uniform across the surface.
Yep.
But
Oh, that's
I guess fluctuations inside the object itself lead to the deformation of the front.
Yeah, give me just a sec here.
While the Rayleigh.
But if you remember the diagram that Tim put up,
Yeah, I'm trying to get that up.
within the interface, as it actually flipped back and forth, rather like a string,
Yep.
you could actually see there were different color densities within it and they were moving around. And so the thing is that this is what I was getting at about when we look at the object, we think, oh, it's fixed in space as far as we're concerned,
Yep.
so maybe the parameters are. The reality is the parameters are changing. So Tim steps through this. The next picture.
Here is the thing to bear in mind is, in this case, what you're looking at is gas pressure acting on the layer. What you're seeing here is there's gas in here, it's ionized, but the ionization pressure is actually thermal. It's not so much where the Rayleigh-Taylor instability is caused by actual motion of fluid. If you like fingers of fluid, for the sake of argument, that's a bad analogy, but anyway, what you're seeing here is that the ionizing body here, the very hot star, is actually driving this gas out, but it's driving it in a bulk, shall we say. It's not going out as a packet of accelerated fluid. It's expanding because of the thermal effects, the thermal pressure from inside. So that, to my mind, is the fundamental distinction.
Yeah, but
that we're
that's-
not accelerating a packet of fluid. Here we're forcing a bulk of fluid to expand. If that makes any sense.
Well, it does, and that's why the pressure is always kind of
Yes.
normal to the surface.
Yeah.
While the other one is in the same direction because it's like a drag.
Yes.
Right? It's always in the same
Yes.
direction. And because of that, but fluctuations lead to these, like.
Thank you. That is perfect. I love it.
But one
And-
has
and
to
that's-
ask. One has to ask why do the Rayleigh-Taylor instabilities give you fingers, whereas this
Because it's a
is-
different type of instability.
Oh, yes.
it's actually to do with the viscosity.
Yeah.
And the thing that determines the shape of these instabilities is the viscosity contrast across the interface. If you have a very strong contrast, imagine, for example, you've got literally water, warm water, trying to drive its way up through warm asphalt.
Yep.
In fact, this actually happens when people lay asphalt down in the
Yep.
wrong conditions.
Yep.
It breaks up because these veins of water come up through the asphalt. It's exactly the same situation, but they're very thin. Whereas if you're making porridge and you've got or actually you've got a really nice thick soup,
Yes, you do.
and you leave it on the hot plate with no lid on, what happens? Bubbles start rising through it and they start spitting all over your cooker. But the bubbles aren't coming up as fingers.
Nope.
They're coming up as big masses.
They're coming up as blobs.
So the thing is that there's much less of a viscosity contrast of warm soup
Yep.
within slightly less warm soup.
Yep.
That's a very small viscosity contrast,
Yeah.
but a huge viscosity contrast between water and warm asphalt. So if in this case here, as opposed to the Rayleigh-Taylor, if this is only a little bit warmer
That's right.
than this,
Yep.
then you won't get the fingers because you've got a very low viscosity contrast. So it starts pushing as a mass, but this is an interface. And all interfaces, as Tim said early on, physically, mechanically, are unstable. And so what it'll do is it will begin to warp. And as it begins to warp, so because this warping will actually
move
be
on.
a periodic
Yep.
distribution of instability, you'll get this wavy interface. Now, what I don't get is why the waves actually grow and then collapse and then grow and collapse
But
again.
actually,
at
I
the
don't
same
see
spot.
them as growing and collapsing. In fact, what they're doing is they're
Oscillating, yep. That part, I can't explain the mechanics of that. But interestingly, look what's happening. This density here
Yes, the
is
density.
variable. Now,
Yes.
what does a variable density do? It affects two things. It can affect the temperature, because we're talking about gas,
Yep.
and it can affect the viscosity contrast.
Yeah. What,
So
what
all
I
of a
didn't
sudden, this
what I didn't
becomes
draw
very
here.
dynamic.
What I didn't draw here. I didn't put on the original diagram that I based this on. Showed arrows showing flow
Yeah.
inside the layer. I left those off because it was just
Yeah.
getting too damn busy.
Too
It
complicated.
was just too busy. But what you're seeing here is the red is the high density. So this is pressing itself into it.
Yeah.
And so there's a tremendous amount of complex stuff happening in here. But what it is also doing is it's shifting, it's propagating this whole, how shall I describe it? We could start off with this in maybe a tiny area, but this could start rippling all the way around the edge of the tulip
Absolutely.
as it keeps going. It's going to start with one little chunk of tulip, but it's going to start radiating all the way along. So you're dealing with a three-dimensional oscillation.
Can we go back to
Yep.
the iris?
Which iris did you?
The big pretty picture of the iris. Oh, yeah, no, the iris nebula, that's the helix.
Iris. Oh, the necklace.
No, the iris. Sorry, the cat's eye. The cat's
Oh,
eye.
the cat's eye.
Yeah. I get my name
The
said.
the cat's pupil. Oh.
The cat's pupil.
The cat's pupil, yeah, I mean exactly the opposite direction
I
where
know.
I was going.
There we go.
Yeah.
This beautifully illustrates what I was talking
Oh,
about.
isn't this gorgeous?
About the variation in physical properties
Yep.
having an impact on what you, as an astronomer, see. Whether you're looking at a Hubble picture or through your own telescope, if you're lucky. And I pointed this out earlier, that in the older shells, this is a younger shell,
Yep.
these are older shells.
Yep.
But you see these radiating fingers here, and you see them up there in the older shells?
Now, not these spikes.
No, don't mean those.
Don't mistake the
These
spikes.
things
Those are artifacts.
Yeah. These are the Rayleigh-Taylor instabilities that Tim was talking about.
Right here.
But here, in the younger bubbles, you've got these cells.
Yep.
So something has happened between the older bubbles and the younger bubbles to change the physical properties of the system so that the instabilities have changed. The simplest way of explaining this from my point of view is to actually reduce the viscosity contrast across this interface compared with the viscosity contrast that existed earlier across these other interfaces.
Yeah.
And the simplest way of doing that is to drop the temperature
Yeah.
inside the later bubbles compared with the temperature in the early bubbles. Now, why this would happen, I don't know.
Well, if you're looking at the later bubbles, though, I mean, these are expanding into 3 dimensions. You're expending a vast amount of energy moving that shock wave out.
It's cooling.
And it's cooling like
And it's
crazy.
cooling, yeah.
One
But
of the
this is what where you want it even cooler. Or you warm the exterior.
Yes.
You warm on the outside of the interface, or you cool on the inside of the interface.
Yep.
But that then gives you these much broader instabilities, these bubble-like instabilities, rather than the finger-like instabilities.
Well, what's interesting is the central white dwarf in this is sitting at somewhere around 100,000 Kelvin. So I mean, this is a monstrously hot. This is one of the hottest white dwarfs known. So I mean, the temperature gradient in there is staggering. But yeah, you are getting a tremendous amount of cooling as it's coming out. An interesting analysis, again, of nuclear detonation. One of the analyses for that, actually, the initial analyses, which is a simplification, was to plot the effect of a heating wave going out and a cooling wave going in,
Yeah.
which is a bit of a fiction, but it does show that you've got cooling effects from the outers.
But don't forget that the equations for all of these instabilities, they have no sense of direction, but
No.
they're relative.
Yes.
And so you could either have the outer mass moving in towards
Yep.
the inner mass, or the reverse. The effect.
That was
It's the
Taylor's
same.
brilliant. That was Taylor's brilliant contribution to the whole thing, was being able to recognize that there was that inverse behavior to it.
Tim, what do you mean by artifacts? That's
Oh,
optical?
these are basically
That's part of the optics.
these are artifacts of the optical system.
Okay.
Yeah, the press release for this made that clear. These are basically sort of like super duper diffraction spikes.
So
They
I
made a
won't
point
get
of that it's purely just.
So I won't get upset with you when I don't see them.
Yes, exactly. Of course, I don't have an 82-inch telescope, so you know. And when I tried looking at this through a 15-inch telescope, the light pollution was awful. I won't get a chance to use it anymore. My 15-inch is gone. Oh, yeah, I operated the museum's 15-inch telescope for years. And I can't do it anymore because it's gone.
So what is the magnification on this particular image?
Oh boy, good question. I don't know. I really don't know. If I find a press release on it, it can probably tell me the field size, but I don't have it in front of me.
I'm trying to think how big my 8-inch would make.
The question is, how much of it are you going to see? I suspect through a small telescope, you're probably going to see only the innermost chunk of it. The outer bits, I expect you're not going to see at all through a small telescope.
With a camera on a 6-inch, you can actually see a couple of the shells.
A couple of them. You're not going to see all of them.
You won't see any of the internal detail in the shell at all. No.
No, it'd be too.
But it's a thrill just to even see the existence of the shells.
Yep.
Any idea what the jets might be?
Which jets? Sorry, the ones.
The jets,
Oh, here to here.
yeah.
The description on it calls them bipolar jets. So I presume what's happening is I'm assuming that this is the rotational axis. There's an interesting thing that's come out of it. This hasn't been confirmed yet, but an interesting thing with bipolar planetary nebulae. And I didn't put that in. Maybe I should have. Do I have a picture of it here? Maybe I do. I might have left. Oh, hang on. I probably put it in the background. Sorry, I'm talking to myself here.
I'm used to it.
Oh, good. Oh yeah, Stormbird himself
Give
here.
some encouragement.
Yeah, don't encourage the animals. Leave that picture. Oh yeah, this is something else. This is the Medusa Nebula. Oh, here we go. This classic one. Come on, load, you silly little beggar. Yeah, this classic, Minkowski's butterfly. An interesting thing has been coming out. It appears, to a first guess, it's still being worked on, that the axis the central axis of these bipolar nebulae seems to be aligned with the plane of the galaxy. And they found this for a huge number of bipolar planetaries, that the principal axis seems to be aligned with the plane of the galaxy to apparently a fairly high degree. There's not enough data to confirm, but yeah, this is one of the, I forget how they describe it, but it's sort of like discretionary time, when there's some time left over and they're doing the analysis. So this is like director's discretionary time at some of the ESO facilities. It's very low on their list, but it's beginning to look like there might be something to the.
Why would that be the case?
They haven't got a clue. They have not got a clue, and they're not even sure that they have enough data to make a statistical. Like it's on that hairy edge where it seems to be a little more than a fluke, but there's just not. The data are too poor. The data set's too poor to come up with it, but it's too enticing to ignore. It's at that lovely state where you gotta look, but it's not high enough that there's anybody willing to do a massive research effort on it. So it's basically discretionary time. Check out a bunch more bipolar planetary nebulas. Interestingly enough, it's bipolar planetaries. It doesn't appear to be bipolar nebulae like the homunculus. It just appears to be bipolar planetaries. But again, the data set is too poor to come up with anything. This is all super early stuff. And when you read the press release on it, it's pretty obvious that some of the guys that were doing it were sort of, why did you come and ask me to report about this? I didn't want to tell anybody about this. You could just sort of see how they're halfway. This could be complete crock. I don't want to ruin my reputation on this crap.
Yeah, it's not at all obvious what the connection would
Nope.
be.
So, I mean, they're perfectly honest, and I mean, this is, again, the perfect example. They're saying, look, I mean, it's enticing, but we haven't got a clue. This could turn out to be statistical rubbish.
Could it be something to do with the galactic magnetic field?
That was actually one speculation, but right now it's all like beer at, this is all, chats over beers at Kelsey's. It's at that level of fun science. this is coffee, donuts, beer, and pizza. It's at that level, but it's a fascinating little thing. But to my mind, it's kind of fun of what you can do with when you've got an interested group of people. This is partly why I used all the ESO pictures, partly because they've got such an incredibly good outreach system, but they've got quite an interesting little pioneering view at the ESO facilities. They're an interesting bunch. They're fascinating.
Tim, this has been from my point of view, this has been an absolutely great presentation because it really corresponds to the spirit of what our workshop series is about.
Oh, good.
Which is as an adjunct to the RASC's understanding the universe, and you've really given us an opportunity here to increase our understanding of what it is we're actually looking at. Because when you do look at something like the Helix Nebula through a telescope, and especially if you do manage to put a camera on your telescope, even small, you can see those radial hair-like features.
You can, yes.
This helps us understand really what we might be looking at.
But bear in mind, as I said, you're seeing me in my astronomical underwear. I mean, I'm learning this. You're seeing me as I'm learning. And I could be dead wrong on some of this stuff. I'm discovering this just a little bit before I'm passing it on to you folks. So I figured this would be a nice, reasonably gentle place for me to do such things. I'm not sure I'd want to do a talk like this to the RSC.
No, I don't think it would work.
No, I don't know.
You need time to go back over and back over and back over.
Oh yeah, this is definitely a cooperative talk. So I hope this has been useful. There's a lot of stuff I don't completely understand about this. I'm learning it just as fast. What I want to share is that, I don't know, I'm a 60-year-old kid, what can I tell you? I just want to, that's what I really want to share here is, I'm no expert, okay? I'm a little geek that goes out and looks through a telescope and says, gee, Ma, this is cool. I don't have much more training than any of you guys do. I just read a lot, and I listen a lot, and I'm happy to take whatever I can get from everybody. The only reason I do this stuff is I learn as much from talking to people as I do from doing it. So I hope this has been worthwhile, and hope this has been worth your time, and that this is something that you felt was good to come out to on a cold December day. And thank you so much for the comments and for inspiring my brain, which needs inspiration, I can tell you.
Thank
Thank you,
very
too.
much for-
Thank you all. And my screwed up PowerPoint. I really had that all nicely planned. I deleted my slide. I was going to push the button and the cow would pop up over the Stromgren sphere. And,
But you recovered so well.
well, like I said, I tap dance.
How did we even notice?
Yeah.
We wouldn't have noticed if you hadn't pointed it out, actually.
Yeah, I think you might have noticed that I was going out of PowerPoint. Anyway,
It's seamless, isn't it?
yeah, perfect. It's seamless if you're blind.
You need to get a young kid to show you like Prezi for you.
That's it. Yeah, it's this.